How's it going, everyone? In this video, we're going to discuss all of these exponent rules and where they come from, and the fact that you don't really need to memorize all of them because they're all just shortcuts. They're all just special cases of the definition of what an exponent is. Now, this happens with a lot of subjects. Students are asked to memorize a large number of rules, and they might mix up what rule is used where and struggle to memorize all of them. But in a lot of those cases, all these rules are just special cases of a very small number of rules. And in this case, there's only just one rule, which is the definition of what an exponent is, which leads to all of these equations you see in front, right? So what we see here is 1, 2, 3, 4, 5, 6, 7, you could consider it 8 exponent rules. Sometimes more are presented. Sometimes with this bottom left one here, people will also write equals a to the power of c and all of that to the power of b. Sometimes people will add the rule a to the power of 1 over b is the bth root of a, right? So sometimes you'll have 9, 10 rules presented, and again, they're all just special cases of what an exponent is. So they don't all need to be memorized. And here I'm going to show you where all of these rules come from, how they all just come from the definition of an exponent. So, what is an exponent? Some number to the power of some other number means you have a string of multiplication where the bottom number appears a certain number of times. The number of times it appears is determined by the top number. Okay, the number in the bottom, the large one, is called the base, and the one written in the top right is called the exponent. And other times it could be written like this, right, where you have this kind of hat symbol and the exponent is written after the hat symbol. It's just two ways of writing the same thing. Okay, so you could write a hat b, or you could write a to the power of b, right? Another way of saying to the exponent of is to say to the power of, right? So you could call this 3 to the power of 4 or 3 to the exponent 4. Sometimes people shorten it and they just say 3 to the 4, and that means to the power of or to the exponent of. And all that means is you have a string of multiplication where the bottom number is being multiplied a number of times. How many times does that bottom number appear? That top number. That's how many times. Okay, so that's it. That's the definition of what it means to raise something to the power of something else. That's what exponents are. All of the rules you see up here are just special cases of this. For example, let's say you have a to the power of b multiplied by a to the power of c. Okay, so based on the definition of an exponent, what does that mean? Well, you have a bunch of a's multiplying each other. How many a's are in this string of multiplication? B of them. That's what this first part means. But then we're multiplying it by a to the power of c. So what's that? Well, that's also a bunch of a's multiplying each other. And how many a's are in this string of multiplication? C of them. That's what that second part means. Okay, so we have this long string of a's in total. How many of them are there? Well, there's b of them, and then there's another c of them. They're all multiplying each other. So we can shorten that as a to the power of b plus c. That's where that shortcut comes from. That's why a to the power of b times a to the power of c equals a to the power of b plus c. So if you happen to forget this rule, you can just derive it from the definition of exponents. But also, knowing where that rule comes from might make it a lot easier to remember because it makes sense now. It's not just some arbitrary rule. It logically makes sense. It cannot be any other way. Now let's tackle a to the power of b divided by a to the power of c. So again, by the definition of exponents, we have a string of a's multiplying each other. There are b of them. And there's a string of c's multiplying each other in the denominator. There are c of them. Now, how can we simplify this? Okay, well, what's going to happen is that a's in the bottom will cancel out a's in the top. And you can keep on doing that until you have some number of a's left in top or some number of a's left in the bottom. Okay, so let's imagine the simple case where b is greater than c. Okay, so for example, some number to the power of 5 divided by some number to the power of 3. Okay, so we have 1, 2, 3, 4, 5 a's multiplying each other. Sorry if these dots are a little difficult to see. And then we have 1, 2, 3 a's multiplying each other in the denominator. Okay, so we start canceling them out. A divided by A divided by A divided by A. We're canceling them out because A divided by A is 1. Right? So what we're essentially left with is A times A equals the answer. Right? A times 1. So what we have is A squared. Right? Because we have two A's multiplying one another. Why are we only left with 2? Well, we had 5 on top, and 3 of those 5 are canceled out by the 3 in the bottom. Right? The exponent of the denominator determines how many are canceled out, so we have 2 left, right? Because 5 minus 3 is 2. Now, that's going to happen regardless of what our exponents are, whether it's 5 and 3 or some other number. Okay? So, in the case of the top exponent being greater than the bottom exponent, we can say, okay, well, a to the power of b divided by a to the power of c is a to the power of b minus c. That just makes sense. It cannot be any other way, right? That's where this exponent rule comes from. It's just a shortcut, a special case that comes from the definition of exponents. Okay, now what happens if the top exponent is actually smaller than the bottom exponent? Okay, what if we have a to the power of 3 divided by a to the power of 5? Okay, so we have a times a times a divided by a times a times a times a times a. Okay, so when we start canceling out, because there are more a's in the bottom, we actually end up with 1 over a squared. Okay, the 1 is on top because we have 3 a's divided by 3 a's. Well, a to the power of 3 divided by a to the power of 3, that equals 1. Then we have 2 a's left in the bottom. So, again, we just have the difference between the two exponents. But because our top exponent is smaller, we're actually dividing by a to the power of that difference. Now, if we follow our rule here, a to the power of 3 minus 5, right, the rule we derived right here, the top exponent minus the bottom exponent, well, that gives us a to the power of negative 2. So what we have then, a to the power of negative 2 equals 1 over a to the power of 2. And again, this isn't just the case with 3 and 5. This is the case with any exponents. A to the power of b divided by a to the power of c, where c is bigger, you're going to have a negative exponent as a result. And what that means is it's just 1 divided by a to the power of that difference. Okay, and that's where we get this rule here. A to the power of negative b, that's just 1 over a to the power of b. Again, that's not an arbitrary rule that was made up. It's just stemming from the logic of the definition of exponents, which gives us this rule right here. And when we end up with the top exponent being smaller than the bottom exponent, we get a negative exponent based on this rule, and that negative exponent means 1 over a to the power of some positive exponent. That's where this rule here comes from. Now, what if the two exponents are equal to one another? Okay, what if we have, say, 3 to the power 4 divided by 3 to the power 4? Okay, so we have 4 3's divided by 4 3's. So, well, that should equal 1, right? Because you have all of them canceling out with the 3's in the bottom. And that's no surprise because you have 3 to the power 4 divided by 3 to the power 4. Something divided by itself is equal to 1. But at the same time, what if we apply this exponent division rule here? Okay, so we have a to the power of b divided by a to the power of b. On one hand, that should equal 1 because it's something divided by itself. On the other hand, it equals a to the power of b minus b, right? The top exponent minus the bottom exponent, which is a to the power of 0. So what we have then is 1 equals a to the power of 0. Anything to the power of 0 is 1. That's where that rule comes from. It just follows from the logic. Now, what if the top exponent is just 1 larger than the bottom exponent? Okay, so you have a whole bunch of a's, b of them, and then another a, right? Because you have a string of a's multiplying one another. How many do you have? B plus 1, right? So there's your b and there's your plus 1. And in the bottom, you just have b of them. Well, so that a to the power of b times a is divided by a to the power of b. Well, the a to the power b's are going to cancel out, and you're just left with a. Okay, now what if we again apply our division rule to simplify exponents, where if you have the same base to the power of something divided by the same base to the power of something else, your exponent is going to be the top minus the bottom. Well, now you have b plus 1 minus b. The b's cancel out because you have b minus b. You just have a to the power of 1. Well, we just determined that that should equal a. So there's your next rule. Anything to the power of 1 is just itself. Now, this is often explained as, well, you only have one of them multiplying nothing else, so it's just itself. Well, and that can be misleading because, well, it's not multiplying nothing. If it's multiplying 0, that's equal to 0. A times 0 is 0. Or people sometimes say, well, you imagine a 1 multiplying everything, so this is just a times 1. And yeah, you can imagine a 1 multiplying everything, but that just makes it easier to believe the rule. It doesn't actually explain why the rule is what it is. This is why the rule is what it is, because it just stems from the logic, right? If you have 3 to the power of 4 divided by 3 to the power of 3, 1, 2, 3, 4 divided by 1, 2, 3. You have your 3 3's cancel out, and there's 1 3 left. So it's just equal to 3. And then if we use our shortcut, that 3 to the power of 4 divided by 3 to the power of 3 should be 3 to the power of 4 minus 3, that shortcut that we derived right here, which just stems from the definition of exponents, well, then that's 3 to the power of 1. So that's not just going to be the case with 3 and exponents 4 and 3. That's the case with anything like we showed here. That's why anything to the power of 1 is itself. Okay, Same with anything to the power of 0 is equal to 1, right? People often think that's some strange arbitrary rule, right? You don't have any a's in your string of multiplication, so you just imagine it multiplied by 1. Why? That sounds arbitrary. You don't have to imagine it multiplied by 1. It just stems from this rule right here. Anything divided by itself is 1, because that's how much times you can fit it within itself. And if we use our subtraction of powers rule, well, that's also a to the power of 0. So anything to the power of 0 is 1. Now, let's handle the next one. Next one is a bit easier than these last couple. A to the power of b, and then all of that to the power of c. Okay, well, let's expand that, right? So we have a to the power of b times a to the power of b times a to the power of b, and so on. We have a bunch of a to the power of b's. How many of them? C of them. That's what the exponent c means, right? Whatever's in the brackets, we have a string of multiplication of whatever's in the brackets. How many times does the thing in the brackets appear? C times, right? A to the power of b times a to the power of b times a to the power of b, and so on, c times. Okay, let's break down every one of those a to the power of b's now. So we have a times a bunch of those. How many of them? B times a, and a bunch of those. How many a's are we multiplying by one another? B. And we just keep doing that, right? A times a times a, b times, right? So we have a bunch of these sets of BA's, okay? How many of those sets do we have, right? And we can put brackets around them if we want, right? How many of those sets of BA's do we have? We have C of them. Okay, so we have C sets of BA's. So how many A's are there in total? Well, a group of B, C times, that's going to be B times C, right? So we have A times A times A, and so on. B times C times, right? So that's going to be a to the power of b times c. And that's where that rule comes from. A to the power of b to the power of c equals a to the power of bc. Now, you can multiply in any order, right? You could also say that this is a to the power of cb, so it's also going to be a to the power of c to the power of b. And sometimes this is presented as two different rules. But again, it all stems from just the definition of exponents. Okay, like if you have 3 to the power of 2 to the power of 4, so you have 3 squared times 3 squared times 3 squared times 3 squared, right? There's 4 of those 3 squareds. So that's 3 times 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 3. How many 3's do you have? Well, you have 8 of them, right? Because you have 4 groups of 2. That's 3 to the power of 8, right? Because it's 3 to the power of 4 groups of 2. That's just an example of that rule. Okay, you have something to an exponent, and all of that is raised to another exponent. Just multiply the exponents. And that brings us to our last rule, which can be presented in different ways. Okay, and that is that a to the power of b over c is equal to a to the power of b, but you take the cth root of that, or the cth root of a, and then all of that to the power of b. So where does that come from? First, we're going to talk about what a root is. Okay, so people are familiar with the square root of a number, right? It's often written like this. That's actually a shortcut. This is the full way to write it. The second root of a number means what do you have to multiply by itself twice to get, in this case, 9? Well, in this case, it's 3, right? Because 3 squared equals 9. Okay, what's the third root of a number? Let's say 8, right? Well, that means what do you have to multiply by itself 3 times in order to get 8? That happens to be a 2. 2 to the power of 3 equals 8. Okay, you can do a fourth root, right? Let's just say the fourth root of 16. What do you have to multiply by itself 4 times to get 16? Well, that's actually 2 again. 2 to the power of 4 equals 16. That's what roots are. Okay, so let's say you have, okay, so let's say that's equal to x. We don't know what that is. All right, well, let's raise both sides of the equation to the power of 4. Okay, well, we know that if we have something to an exponent, we raise that to another exponent. That's just multiplying the exponent. 16 to the power of 1 over 4 times 4 equals x to the power of 4. So 16 to the power of 4 over 4 equals x to the power of 4. So 16 to the power of 1, which we know is just 16, equals x to the power of 4. So what's x? X is something you have to multiply by itself 4 times in order to get 16. In other words, x is the fourth root of 16, right? So x is the fourth root of 16. But what did we start with at the top? X is 16 to the power of 1 over 4. X is 16 to the power of 1 over 4. So the fourth root of 16 is 16 to the power of 1 over 4. Now that's not just the case with 16 and 4 and 1 over 4. It's the case with anything. A to the power of 1 over b is what? Okay, well, let's raise both sides to the power of b. Which means we have a to the power of 1 over b times b, which means a to the power of b over b, which means a to the power of 1, which tells us that a equals x to the power of b. So x is what? X is something you have to multiply by itself b times in order to get a. Right? So x is the bth root of a. Okay, but what do we have on top here? That x is also a to the power of 1 over b. They're equal to the same thing, right? So a to the power of 1 over b is just the bth root of a. Okay, so what if we then have a to the power of c over b? Okay, well, that's a to the power of 1 over b to the power of c. So that's just the bth root of a, and then all of that to the power of c. Now we could also write that as, well, this is a to the power of c to the power of 1 over b. And again, the reason that works is because of this this multiplication rule of exponents, right? And I'm going to write that out a little longer just in a second, right? So this is a to the power of c, and then the bth root of that. And that's where that final exponent rule comes from, right? So let's say we have, now we represented it as a to the power of b over c at the very, very top. Right? This rule right here. Right? So this one we already showed. Okay, so that longer one, let's go all the way to the bottom now. So this is a to the power of 1 over c times b. So when you have an exponent that's something times something else, that could be the base to the power of one of those factors and then to the power of the other factor, right? So we could think of this as a to the power of 1 over c. 1 over c I meant to, right? And then to the power of b, which means it's the cth root of a to the power of b. Or we can think of it as a to the power of b and then to the power of 1 over c. in which case it's a to the power of b, and then the cth root of all that. Okay, so for example, 9 to the power of 3 over 2, you can think of that as, well, that's going to be the square root of 9 raised to the power of 3, right? So 3 to the power of 3, which is 27. Or you can think of that as 9 cubed and then the square root of 9 cubed. Well, the square root of 9 cubed is also going to give you 27. It's going to be the same thing. So that's where all these rules come from. You don't need to memorize all of them. They're just special cases of the definition of an exponent. But just knowing where those rules come from, that they're not arbitrary, and having that definition of an exponent in mind, it makes it easier to remember all of those rules because they all make sense now. So I hope that helps, and until next time.